I welcome back all to the course on control system engineering. In this video, we are going to learn the basic concepts of block diagram representation of a control system. After that, we will learn the reduction techniques of block diagram with the different reduction techniques. Before going to the block diagram representation of a given control system, let us discuss what is meant by block diagram and why to reduce the block diagram. The block diagram is nothing but it's a graphical representation of a physical system by illustrating the relationships among different components. In other words, you can also say the block diagram is a pictorial representation that gives the relationship between the cause and effect. Here the cause is nothing but the input and the effect is the output. And the block diagram in general is represented by a small box, a rectangular box. And the inside content of the box gives the relationship between the input and output variables. The signal flow of the input and output variables are indicated by the arrow marks. As shown in this figure, X is the input, Y is the output. So the arrow mark is represented. Input variable is coming to the block, and the output variable is having the outgoing arrow mark. The inside content in the box or block is given by d by dt. Here nothing but the relationship between x and y is the derivative term, differentiative. That is y is equal to dx by dt. This is the way we can represent the input and output relationship in a pictorial way. This is nothing but block diagram representation. This is a simple example. For some cases like addition, subtraction, there is a special kind of representation. Instead of keeping a box, we can use a small circle which is having different inputs, number of inputs, maybe 2 inputs or 3 inputs with their signs. In this example, x and y are the two input signals, and those two signals are having plus sign. So the block here, the circle summing those two signals and giving the output signal as the algebraic sum of these two signals, that is x plus y. That may be subtraction. The same kind of representation you can also use for the subtraction. When the sign of the one of the variables is negative, then the output variable is equal to the subtraction of these two variables. Here in this example, y is having negative sign, therefore output of the subtractor is equal to x minus y. The same circle symbol is used both for the summing and subtractor. So in general you can say this circle is the summing point, because based on the sign we already getting the output is sum of the inputs or subtraction of the inputs. So a small circle we can say it as a summing point. The sign indicates the difference. And sometimes you can have 3 inputs, more than 2 inputs you can use for the same summing point. So the output is the sum of these input signals. The sign decides either it is addition or subtraction. Sometimes this summing point can also use represented like a circle inside the cross mark. Anyway you can use it. Both are correct representations. Now we'll see the components of the block diagram in linear time invariant systems. In general, what are the components we have to represent any system in a block diagram way? Here we have four major components to represent a system in a block diagram way. First one is the signal. Definitely a system is having a signal. So Signal is the first and basic component of a block diagram. And second one is system or block. So a block or a system represents the relation between two or more signals. And third is the summing junction. As already just we have seen, the summing point or the summing junction combines two or more signals, maybe addition or subtraction. We can use this junction as a summing point. And last component is pick off or take off point. I'll show you an example about this takeoff point here. Okay, I'll show you one by one. So let me tell what is meant by takeoff point here. The takeoff point in general used to combine the same kind of signals in different ways and represent in a single line. Sometimes we have the same amount of signal from different lines. If all these signals are coming at a point, that output line also will have the same signal. That is nothing but a takeoff point. Of course, anyhow, I'll show you a diagram of the takeoff point, then you can clearly understand. So, see the first figure A shows the signals. In general, any block diagram is having the one input signal and one output signal. Of course, in multiple input, multiple output will have number of inputs and number of outputs. But in general, in a single input, single output system, we have one input signal and one output signal. So here in general, R of S is taken as the input signal and C of S is taken as the output signal. Therefore, a system or a block is represented by a rectangular box with input R of S and output C of S. And inside the box, G of S represents the relation between C of S and R of S. Here in general, this box in Laplace transform representation gives the transfer function of the system. And in C figure, you can see the summing junction. Different signals coming to the summing point, and all these are added or subtracted based on their sign. And fourth point is this pick off point or take off point. Here in the figure, you can see clearly the pick off point is nothing but the RFS signal is coming to the point, and at this point, this RFS is splitting into three lines. Any number of lines can split this same signal to give the same signal for different signals, different systems. So this pick off or take off point is useful where we need to apply the same signal for number of systems. We have to split this signal equally. Same signal we have to send in three lines for three systems. There you can use this takeoff or pick off point. So this is one more example of takeoff point. Either one signal split into three lines or three lines combined at a point to give the same signal. Here we are not adding these signals and we are not dividing these signals. We are taking the same signal and making available the same signal at three lines. So in the same way, in the three lines, same signal are combining and getting the same signal to a single system. This is nothing but the takeoff point. Let us see one example of an LTI system to represent in a block diagram way. Here it is given, the expression is given, the LTI system expression is given as x3 is equal to a1 x1 plus a2 x2 minus 5, where x1 x2 x3 are the variables and a1 a2 are the coefficients and phi is a constant. In this, by this expression, you can clearly understand that x3 is the output variable, x1, x2 are the input variables, and a1, a2 are the coefficients of x1 and x2 respectively. And also we know that we can understand that x3 is a combination of three terms. First term is a1x1, second term is a2x2, and third term is minus 5. So to represent this model in a block diagram way, we need a summing point, and the summing point must have three inputs. So let us see the pictorial diagram of this LTI model. So see, this is the model where the summing point is having three input signal. First one is a1x1 and it is having plus sign. Second is a2x2 having plus sign. Third signal is 5 having minus sign. Therefore x3 is equal to a1x1 plus a2x2 minus 5. And here a1x1 signal may not be directly available. We have the inputs like x1 x2 only. Then how to get a1 x1 signal? It's very simple. X1 must be multiplied with a1 coefficient. So this is the representation of a1 x1 again. So a1 x1 is obtained by multiplying x1 with a constant with a coefficient a1. This way a2 x2 we can represent the similar way. Therefore, finally, the block diagram representation of the given LT model is this one. A1, X1, X2 are the input signals of the total model, and also 5 is a constant, of course, but the input variables are X1, X2 only. And X1 is given to A1 block, so that we are getting A1, X1, that is given to the summing point. Similar way, X3 is multiplied with A2 block and getting A2, X2, that is given to the summing point. And finally, 5 is directly given to the summing point. Therefore, x3 is a combination of these three terms. This is the way of representing an LT model in a complete block diagram way. So here the blocks are two multipliers a1, a2 and one summing point. And let us see the second example. Of course, it is a general x1, x2, x3 and so on, xn minus 1 number of variables are there, and we want to get the output variable xn, and again it is like a weighted sum of the input variables with the coefficients a1, a2 and so on, an minus 1. In a similar way, we'll have this kind of block diagram. And suppose if we have the non-linear relationships like dx1 by dt and integral of x1, then how to develop this? Of course, this is also very simple. Here a1 is multiplied with the derivative term. First, take the x1 variable as the input and take a block which is having inside d by dt relation, and the output is nothing but dx1 by dt, and you multiply this output with a1 block. Similar way, second term 1 by b is multiplied with integral of x1 dt. So box is having integral of dt. So the input is x1. Similar way, you try this example for your practice in a similar way. Now let us see the topologies in how many ways we can represent this block diagram of a given system. In general, we will have number of subsystems in a system. Each subsystem will be having a small uh, transfer function, and the final transfer function will get by multiplying all these subsystem transfer functions. This is nothing but the cascade connection of the blocks. So final G, the transfer function of a system is given by G1, G2, G3 and so on Gn, because all these are connected in series or cascade. This is an example of a cascade system. Here G1, G2, two subsystems are connected in a series or in a cascade, then the output C is equal to the multiplication of these two G1 G2 into the input E. So the total overall system transfer function is equal to the product of these two subsystem transfer functions when they are connected in cascade. This is and one more example where two subsystems are connected in cascade. Here G1, after G1 the output is equal to G1 into R of S. After crossing G2 of S, it is the multiplication of G1, G2 and R of S. After crossing third block, it is the product of G3, Z2, Z1 and R of S. So therefore, after simplification, these three blocks combinedly can simplify and represent it as a single block. That is, the single block transfer function is G1, G2, G3, the product of these three transfer functions. This is the way how we can reduce the block, reduce the system when the subsystems are connected in cascade. Suppose if the subsystems are connected in parallel form, how to reduce this? How to simplify this? Simply, so parallel form is nothing but how to confirm the parallel form first. Of course, in the cascade form, all the blocks are connected in series, so the arrow mark signal flow is from starting to ending. Whereas in parallel form, the input is given to the number of subsystems at the same time, and the arrow marks you can see in the same direction, and also those two subsystems are giving the outgoing signals in the same directions at the input side and output side of the two subsystems, and these two subsystem outputs are combined by the summing point and giving us the output. This connection is nothing but parallel connection. So keep it in mind that parallel form the inputs arrow marks and the output arrow marks must be same direction, then only can say these two systems are connected in parallel form. Now how to reduce this, how to simplify this? If the number of systems are connected in parallel, what is the combined response, combined transfer function? When these three are connected in parallel, see R of S is given to G1 first, therefore we got R of S into G1 of S. When R of S is given to G2, then it is R into G2. When R is given to G3, it is R into G3. All these are combined by the summing point. Therefore, the output is equal to sum of these three. Or if you take common, R of G1 plus G2 plus G3, we will get. Therefore, the combined transfer function or overall transfer function is the sum of these three subsystem transfer functions. So finally, it is G1 plus G2 plus G3. Of course, this plus or minus is depending on those blocks signatures to the summing point. Now, next and last topology of the block diagram is the feedback form. When a feedback is connected, of course, see, first R of S is given to the G1 of S through the summing point, and after getting the output, that C of S is again feedback to the input side. This is nothing but feedback form. There, G1 is continued in forward path and G2 is continued in feedback path. This time, how to reduce the transfer function, overall transfer function? It is simple. It is given C of S. See here, let us see the characteristic equation of the feedback control system. We have already got the transfer function of the given feedback system, and it is in the form of C of S by R of S is equal to G of S by 1 plus or minus G of S into H of S. Here this is also called the control ratio. So it's simply nothing but the control ratio is the closed loop transfer function of the system. And here the denominator term 1 plus or minus G of S into H of S indicates the characteristic equation of the system. From this equation we can get the poles of the system, and we can control the pole locations, so we can have the control phenomena of the system. So it is called from the control ratio. The characteristic equation is getting by equating the denominator part to 0. So the denominator of the transfer function is equal to 0 is called the characteristic equation. And how to represent the feedback control system in the canonical form? It's nothing but already we have seen the control transfer function of the feedback system is already in the canonical form. It represents the terms of s in the order, in the descending order. So when you represent the system like a numerator and denominator, it should be in a order in the power of s. So this is the canonical form, and this represents the simple representation like a summing point having two or more signals, and a simple forward gain and the feedback gain. So this is the canonical form representation of a feedback system. And from this block, from this form, canonical form, we can calculate different parameters like what is the forward transfer function. Here it is G is the forward transfer function, and what is the feedback transfer function, like feedback gain H. And what is the open loop transfer function? This is the sum product of forward and feedback gain. So total G into H is the open loop transfer function. And what is the control ratio or closed loop transfer function? Already we have seen C by R is the control ratio. And what is the error ratio? E by R, error to input signal. This is E by R, that is nothing but 1 by 1 plus or minus GH. And what is the primary feedback ratio? So B is nothing but the feedback signal B, which is equal to C into H by the R. So it is giving GH by 1 plus or minus GH. This is all these parameters we can find when we represent the block diagram in a canonical form. So this is the canonical form representation of a feedback control system. And here plus or minus, always we are giving how to make sure that is it plus or minus in which situation, in the situations. Here this positive and negative sign indicates the feedback positive or negative. If you want to take the positive feedback, keep it there plus. If you want to take the negative feedback, put minus there. So this sign indicates the positive feedback or negative feedback. So for a system, it will be either positive or negative. Both is not possible. Now, how to calculate the parameters when you represent a system in a canonical form? Say for example, this is the system. Of course, it's very easy to calculate if you simplify this feedback control system. So these are the parameters from this system we have obtained. Open loop transfer function, as I know, as I told you already, feedback open loop transfer function is the product of G and H, where G in the example is k by 1 plus k into s plus 1, and H is 0.1. If you multiply these two, you will get the open loop transfer function. Of course, here I have not mentioned the answer. It's very simple to calculate this. Please, you can practice it. And feed forward transfer function is only the G of s. Simply this G of s block we can place in there. Then control ratio is the oral transfer function. Of course, G and H is given. So oral transfer function is given by G of s by 1 plus G of s into H of s. Here plus only is given because we have clearly mentioned the negative feedback. And feedback ratio B by R is given by G of s into H of s by 1 plus G of s into H of s. And error ratio E by R is equal to 1 plus G by G into H. That is, we can substitute and simplify this. Then closed loop transfer function C by R, already we know G by 1 plus G into H, and characteristic equation is 1 plus GH is equal to 0. And closed loop poles and zeros, if k is equal to 10, substitute k is equal to 10, and then we can find the overall transfer function c by r is equal to something numerator in s domain and denominator in s domain. Make numerator is equal to 0, so numerator polynomial is equal to 0. Then find the s roots. Those s roots are called zeros. And similar way, if we make the denominator polynomial of transfer function is equal to 0, the roots of this denominator polynomial are called poles. Then characteristic equation, from this characteristic equation we can find this control ratio, and we can also, by simplification, we can also find what are the poles and what are the zeros, and already we have just discussed. So take that example and solve it, you can clearly understand how to calculate these parameters. And unity feedback, after, of course, after feedback system, always not to be, no need to be mentioned that h block. Sometimes it's like a directly given, that's the feedback signal to the summing point, that indicates the feedback. It doesn't mean that feedback is not there, feedback is there, but the gain or h value is equal to 1. That is nothing but unity feedback. So this is called unity feedback system, where h value is equal to 1 in the feedback. So feedback gain is equal to 1. This is unity feedback system. And sometimes even there is a feedback gain, sometimes we need to forcefully make the feedback gain is equal to 1. So how to make this? Like this. Here this is the given system. Here feedback gain is given h value, but we can make it, this feedback gain is equal to 1 by altering something, by doing something like h. Here you can keep one more block, extra block, with the gain 1 by h, and here this gain is modified to g into h, and therefore this gain made to 1. So if you make like this, is it correct? So question may arise. So let us cross verify. Here what to get, c is equal to c into h, here it will come, and overall gain we know already, g by 1 plus g into h. Here also see this, the signal here is r in r by h, and if you take this like if we simplify this feedback, we will get gh by 1 plus gh, right? 1 plus 1 plus or minus, say here plus or minus given, so it is plus or minus gh. Now this is this loop gain, and it is multiplied with 1 by h. So if you multiply this with 1 by h, what will come? It is multiplied with h. Therefore if you multiply this to h will be cancelled, so again it will be 1 g by 1 plus or minus gh. So it is nothing but, it is equal to this circuit. So this is the way you can make it, the feedback gain is equal to unity, even there is a feedback gain. In some cases it is required depending on the application, so there we can use this kind of transformation. Before concluding this session, let me recall what we have learned in this video. In this video, we have learned what is meant by block diagram and how to represent a block diagram for the simple examples of a system. And we also have discussed or learned different topologies of the systems, control systems. And we also learned how to represent the feedback system in a canonical form, to calculate different parameters from the system which are useful for further study of the behavior of the system. So in this video we have learned the basic concepts of the block diagram to reduce and simplify the total complex systems in further videos. So we'll see in further videos the block diagram reduction techniques and how to simplify the given complex system in a simplified manner. Thank you.